I've been asked to talk a little bit about the frontiers in astrophysics and cosmology, and I decided to put the background of my presentation. This beautiful, it's one of my favorite images of the Hubble Deep Field that shows one of the first images that we ever made of our universe, showing that indeed in every little dot of our universe we see this gigantic amount of galaxies. So we're going to go there. So I start with this nice depiction of what we know about our universe so far. So as Professor Corcomedes said, there's still a lot to present it today. There's still a lot to be understood, but a few of our theories, a few of our scientific ideas are presenting good and encouraging results on where we want to go or how to understand what we see and what we don't see, but we know it's there. So we know that the universe, if it is all, we also don't know, maybe there are hundreds of other universes out there, but the one that we can see, the one where we live in, has begun with a soup of particles that slowly transform themselves into atoms, molecules, and the first stars, which couldn't have any planet with life on it. But they were just basically made out of hydrogen and a little bit of helium maybe. And those stars had to evolve, and through their evolution, other elements of the periodical table could form. And indeed, all the chemical elements that we know are either produced on Earth and they're synthesized, or they were produced on stars. So we are all the remains of stars. We are made of star dust. And not being romantic here, it's really the truth. We are all made of stardust, and everything that you see in your houses is made of that. So we came from the universe. There is no doubt about that. We also know how we have some ideas on how the first galaxies came to be, although there is some debate on how would it be possible to have such gigantic galaxies as we see in the past of our universe, as we do know exist. We do have a very nice theory about the life cycle of stars, how they evolve, and if you didn't know that, stars are born, they have their life cycle, and they die, and according to the quantity of material, to their mass, the cycle of life is a little bit different. We know how stars could form planets, and how a planet could be a rocky planet in a habitable zone of their planet, and how this planet could harbor life. We know we exist, and so we have a fairly good idea on what were the physical phenomena that had to take place in order for us to be here. So this is just a tiny bit of all there is to know. And if we're talking about frontiers in astrophysics and cosmology, everything is a frontier because there's so much that we still don't know. Maybe all the physics as we know it can be challenged by a small little discovery that we can make tomorrow. Maybe one of your students will make this discovery, and this can change our perception, our understanding of the universe as we know it. So everything that I'm presenting is kind of frontiers in astrophysics and cosmology, especially if you understand that many of the discoveries that really completely revolutionized everything we know were less than a century ago. So I can show you some images from the Hubble Space Telescope. This is a gallery of pictures done with the Hubble Space Telescope. Of course, there is always a touch of an artist, changing the colors a little bit and the brightness and contrast so we can see the beautiful things the universe entails. But you have to remember that these pretty pictures were just possible since the 70s, when the Hubble Space Telescope was put on the sky, and actually the Hubble was much later than that, with the Voyagers and the Pioneers, that we started receiving these nice images of our universe and started enhancing our understanding of our cosmos. So we know for sure that we are made out of gas and dust, as I already said. We know for sure that there are stars out there billions of them. And this is just with one of my favorite open cluster, is a cluster of stars. Every little dot that you see here is a little star. Many of them, if not all of them, have planets around them. And this is just a tiny little bit in our sky that we can try to see naked eye, but it's very difficult. It's for those of you, and I think it's most of you from the northern hemisphere, you cannot see this. This is something that we can see in the southern hemisphere, and it's really, really a beautiful open cluster to be observed. But remember, just a tiny nothing in our sky can harbor this many stars. So this is like overwhelming. We know there are planets out there. We live in one of them. And we know that our sun is a star. And one of the things that I'm very fundamentalist about is the sense of scale, which usually textbooks try to kill. And this is something that is important, to make sure that people understand how tiny our planet is. And maybe if it wasn't like that, if it was bigger like Jupiter, we wouldn't be here. So size does matter. And there are other things that I could talk about in that direction, but I'm not going to have time to do that in this talk. But we do know that our sun is a star. It's a very small star, but it's the closest to us, so we can see in more detail. And here I present you just one image. It's just scenes of the next chapter. It's part of one of the demonstrators that we are going to share with you during these weeks, where you get to understand a little bit better what are the spots that we see in the surface of the sun. Sometimes we can even see it with naked eye. Well, don't take me wrong, you shouldn't look to the sun without a proper protection. And that protection is, filters that are really prepared for you to filter 99.9% of the brightness of the sun. But if you have those, you can look at the sun, and sometimes when the sun is active, you do see the spots. So what are they? And what can we learn from them? So this is part of what you're going to learn during this weeks with us. I can give you a question and put a question here. Do you think that the sun rotates around itself? So these are things that we're going to be exploring with you during these days. We know that we live in this beautiful planet. It's the only planet in the solar system, the only place that is good for us to be here. And we know that this planet harbors life. So I put this picture here, not because of the astronaut per se, although I'm always amazed to see that an astronaut can have such a beautiful view, but I would like you to observe that it's daytime on planet Earth, and the sky outside our atmosphere is not blue, as many people say and many textbooks say. The sky outside our atmosphere is dark. So think about that a little bit and how many things you can teach to your students because of that. We do live, as I said, in the habitable zone of our sun, our star, the sun, and the place where liquid water exists. And this is very important to us. We also live in the habitable zone of our galaxy, where the elements are proper to the emergence of life. So these are important questions that we have when we are looking for life outside of the solar system. So many conditions have to be in place for life to emerge. Although we do think that this is a very common thing, that life is out there, we still haven't found it yet. So we do live in a galaxy called the Milky Way, the one galaxy that we cannot make a good picture because we are in it. We live like 26 light years away from the center of the galaxy, which is good, otherwise we wouldn't be here. And we are part of a group of galaxies that is called the Local Group. It's a very tiny group of galaxies, the Local Group, and the Milky Way and Andromeda are the largest galaxies in this group. But the Local Group is part of the Virgo cluster, which in its turn is part of the Super Virgo cluster. So there are gigantic clusters of galaxies, and all of this is part of an even bigger superclusters. As you can see here, I show you a collection of superclusters, so you can see how far I'm going with this. And this is what we call the observable universe. This means that if the universe is, as we consider it to be, 13.9 billion years, this is all we can see. We can only see galaxies that are that far away from us. We know for sure that the universe is much bigger than that, because the galaxies that we see in the edges of our observable universe are receding away from us for 13.7 or zero 0.9 billion years. So during all this time, they're going further and further away, and we cannot see that. So for sure, the universe is much bigger than what we can see. The thing is that it says, oh, well, we don't know that. What we know, and but there are plenty of scientists studying and trying to understand a little bit better what is out there. But what we do know, as I said, is that we do have billions of galaxies surrounding us. And this picture, as I said in the beginning, is one of my favorite ones, where you see, in this picture from the Hubble Space Telescope, all the little dots, with one or two exceptions, are galaxies. And some of them are 13.2 billion years away from us. Well, how do we know that? We know that because we study the spectra of stars. And by looking at spectra of different stars, we can see, we can try to find the objects in the different parts of their life cycle. So here is just a depiction of what we think is the life cycle of a star, and what happens if it is a sun-like star, so if it is a small star, or if it is a massive star that will end up their lives as a black hole. So the way to make sure that this is a good theory, we try to find objects in the different stages that are predicted by this theory. And we do find, I'm only going to show you a few ones. This is, for instance, a giant nebula that is like, it's more or less 163,000 light years away from us. So this beautiful picture taken by the Hubble Space Telescope is 163,000 light years away from us. Or this one, which is an open cluster, and the stars that are forming in its heart. Or this ring nebula, which is the end stage star like our sun. Or this Crab nebula, which is the end stages of a star like a massive star. And this one in particular, we know that it harbors a neutron star in its heart. But also, we know that it's not what you see is what you get, because most of the electromagnetic spectrum is something that we cannot see in the optical. We cannot see with our eyes. So the information that we can retrieve can be collected in several different wavebands, like radio, infrared, ultraviolet, X-ray, gamma ray. So all of these are pictures of the same object in different wavebands. And this provides us a lot of information. For instance, in radio, we can, in a few years ago, the ALMA telescope made this amazing picture of a planet forming disk around a young star. And this was the first time that we could see with this clarity how we think planets are forming around stars. We know now more than 4,000 exoplanets that were discovered by telescopes, which, if we consider that all the stars in the universe, or most of them, should have planets around them. And this gives you an idea of the distribution of the Neptunian-like planets, the gas giant, the super Earth, the terrestrials. So it's more or less an idea. And this picture is not even updated. So there's more out there. And this is showing the method with which they were discovered. So direct imaging, microlensing, transit, radio velocity, timing, maybe all jargons that you don't know, but by the end of this course, you will have a better idea on what it takes to discover an exoplanet. So I show you this picture. You wish this was a picture of an exoplanet that we have discovered, right? No, sorry, you will be very disappointed. Nothing like that. Because, you know, making an image of a planet around another star is really, really very difficult. And for that matter, if you take a look at this image, you see I'm pointing to Earth there. And we are inside of the solar system. This picture was taken by the Cassini mission when it was orbiting the planet Saturn. And still, we barely can see the Earth. And we are very inside the solar system. So think about the size of things in the universe and how difficult it is for us to discover things. And by the way, you are all in that picture. So one thing that I can ask you is, what if you could be the one discovering an exoplanet? You could be you know, pointing your telescope to something and observing a star that does have a planet orbiting it. And that is not a rare thing, it's a very common thing. So this is one of the things that we'll be doing with you during these weeks. You will learn how to discover an exoplanet that is orbiting another star. We will also navigate with you through Einstein's universe. You won't discover everything there is to know because it's a gigantic universe, but it's an amazing one. A universe, which the one we live in, where time and space are relative and they don't really behave as we think they do. There are very strange things happening out there. And this theory, the Einstein's theory of general relativity, was proved, and last year we celebrated the 100 years of the first evidence, which was during a solar eclipse, that Arthur Eddington, a British scientist, during the war with the Germans, have proved a theory of a German scientist proving that science is above everything. And he, with his observations, he gave the first strong evidence that Einstein's theory was right. And that theory brings us many interesting things. First of all, gravity is not a force. It's the consequence of the bending of space-time. That we only can see things that are in the past, and we can see things that are not really there. Like, for instance, this beautiful picture of this Einstein ring, that's how we call it. You see that the face, the depiction of the face of this, this face here, these are galaxies that are distorted. And this distortion is distributed across the face of this, these are other two galaxies, and these are distorted galaxies around it. And the galaxies is in none of this, it's behind it. So it's one of the consequences of gravity. So I could go on forever. I could go on also showing you that Einstein helped us understand in his theory more about the universe. I can tell you that, for instance, that only in the 20s, we discovered that the solar system is located in a galaxy. Only in 1923, we discovered that Andromeda is another galaxy. We didn't know there were galaxies out there. It's less than 100 years ago. In 1929, Hubble, for the first time, made an observation that enabled us to understand that the universe is expanding, which is, okay, there are galaxies out there, there are plenty of galaxies out there, and they're receding from us, they're expanding away from us. And in the 90s, 98 more precisely, we discovered that in fact, Hubble didn't have the whole picture. They are going away from us, but faster and faster. So the expansion of the universe is accelerating. All of this is surrounded by debates, and every time we launch a new mission, the numbers are changed. So there's a strong debate going on what are the correct numbers, and what if, and if the universe expansion is accelerating or not. So these are cutting edge parts of our cosmological understanding, and your students can be working on that one day. I hope they will. It's a fascinating topic. Well, what if I could tell you that you can reproduce all these calculations and you can calculate the age of the universe yourself with your students? Again, something that you are going to be learning with us during this week. There is a specific exercise that helps you reproduce these observations and these calculations of the age of the universe. We also debate what's the shape of the universe. And for that, we use several important missions, but one of them is the study of the cosmic microwave background radiation. And you see here the evolution of the missions studying this microwave radiation, which is in layman's terms, a picture of the universe when it was a baby. So we have now equipment that are capable of making, of depicting the universe, the infant universe. So the evolution of this image is like the evolution of the baby that you see below. So the better the equipments are getting, the better image we have. And now these equipments are showing us that the universe is probably flat. Not our planet. Our planet is not flat, but the universe might be. We don't know that yet. We also have the discovery of gravitational waves that is presenting to us a reality that we knew could be there as a result of Einstein's gravity, and that is opening to us a whole new library, a whole new language to understand the universe. Oh, whoops, that shouldn't be my topic. I'm not going to talk about that. You are going to have a presentation just about gravitational waves. Again, another topic that you will be exploring with us. Well, black holes is another consequence of Einstein's theory. He didn't like that, but they were there and there were no way to avoid them. And now, for the first time, very recently, the Event Horizon Telescope made this first picture of a shadow of a black hole cast in its accretion disk. It's an amazing picture, an amazing feat. And gravitational waves are also helping us better understand where these objects are, and it's a very strong evidence that they do exist. So in this picture, I'll show you more or less the number of black holes that we know exist. It's a very little number if you consider the size of the universe. And the reason for us not having more is because it's very difficult to find them. But what if I told you that you can reproduce the discovery of one of such objects yourself? And this is something that you will be learning with us as well. This is the object that you are going to be exploring with us. Is a stellar mass black hole candidate, and you will, with us, reproduce the light curve of this stellar mass object, and you will understand why it has the shape it has. And it's an exercise that you can apply in secondary school and calculate the potential mass of this black hole candidate, or you can just do with 7th graders, just showing them how we know something is there just by observing a picture. So this is an example of students that have been doing this exercise with us. And with that, I think I have used all my time, but I just wanted to leave you with this message that we do live in a very magical place. We don't need to find things that are not there or non-scientific. You know, there's plenty of magic to be discovered. So make sure you value the place where you live every day. Thank you. So I will stop sharing my screen and then check to see if there are any questions for me.
Thank you very much, Rosa.